Dennis Coyne of LIGO. On stage.
So, you've heard an astronomer give a nice talk about the internet. Now you'll hear a mechanical engineer talk about astronomy. So I'm going to try to do justice to representing the group that I'm a part of, the LIGO Scientific Collaboration. Who are they? There are 1,300 members that cover 123 institutions and involve 20 countries. I'm from what's referred to as the LIGO Laboratory. This is run by Caltech, the California Institute of Technology, where I am, and MIT, the Massachusetts Institute of Technology. We jointly manage for the National Science Foundation the LIGO effort. So let me start. I'm a tinkerer, but let me start with the thinkers. In 2017, the three founding people for our project, Professor Ray Weiss at MIT and Professors Kip Thorne and Barry Barish at Caltech, won the Nobel Prize for the discovery of the first direct detection of gravitational waves from the in-spiral of two black holes that combined in a cataclysmic event. The signal is shown here on the right in comparison to Einstein's general theory of relativity, and they match beautifully. This event, which as you can see from the time scale, is only a fraction of a second, order of a half a second. This chirp signal, which went up in frequency and in amplitude, was a result of two black holes, each about 30 solar masses, combining into one larger black hole. And in the process, liberating 3 solar masses of energy through E equals mc squared. So for this half a second, it was the brightest event in the universe. This is a calculation using Einstein's theory, showing the two black holes spinning around each other and then combining. And you can see gravitational lensing occurring as well. So we only see this event when it happens, when it chirps, just in its final death spiral. Then in 2017, another event, in August of 2017, we detected for the first time the merger of two neutron stars. Neutron stars are the remnants of supernovas. And again, these two objects were spinning around each other until they combined. And we saw this long chirp, this is on the order of a minute, with our detectors, essentially in temporal coincidence with orbiting gamma ray telescope or satellite systems, Fermi, that together with our colleagues in Virgo, which is the European Observatory, Gravitational Wave Observatory in Cascia, outside of Pisa, we localized it to this region of the sky, and then astronomers using optical telescopes searched, and SWOPE telescope managed to find a new object in that region. So this is the first event that opens the field of what we call multi-messenger astronomy. This is a simulation from NASA Goddard, showing the neutron stars in-spiraling. In Newtonian mechanics, this would just go on forever. But the system loses energy through the emanation of gravitational waves. And Gravitational waves are distortions of space-time. In this particular event with neutron stars, it was predicted, and we have now observed, the jets that you see here spewing out material as they combine. It's still undetermined whether this is now a bigger neutron star or a black hole. So this event, whereas the first one had a paper with 1,000 authors, this one had 3,500 authors, to give you the scale of the project. This involves 70 telescopes worldwide, both orbiting and on the terrestrial, covering X-ray, UV, visible, IR, and radio. It's still being observed. So what else can we detect? Well, there's a catalog of possible astrophysical gravitational wave sources. There are other, what we call compact binary systems like neutron stars and black holes that have yet to be observed. And there are other transient phenomena like bursts that, and as well as the stochastic background, the equivalent to the background created from the Big Bang. There should be a gravitational wave component. Right now, our catalog that's been published from our first run is shown here. These are 10 black hole combinations. It's expanded the population of black holes that we now know to exist. Excuse me. And we have one neutron star binary pair that we've observed. We're now in our third science run, and we have, in the first 2 months, issued 17 public alerts. Astronomers all over the planet are busily trying to find what we hear, effectively. We hear it, we don't localize it very well in the sky often. Depends on where it is in the sky. So we're in this run, and it will continue for a year. So we're building a global network. I mentioned our interferometers, LIGO Hanford Observatory in the state of Washington, LIGO Livingston Observatory in the state of Louisiana. Virgo is in Italy. There's a German-British interferometer called GEO, which is not as sensitive, but it's a testbed for some of the enabling technologies. The Japanese have built one they call Kagra under a mountain. It's underground. It also uses cryogenic technology to try to push the sensitivity. And we have begun to build one in India. So what are gravitational waves? They're transverse quadrupolar waves. It's sort of like an electromagnetic wave, but it's not generated from a dipole moment. It's from a quadrupolar moment. They're extremely weak. The strain, that is the stretch in space-time, goes as the inverse of the distance to the source, and as the inverse of the fourth power of the speed of light. So it's extremely weak. To put that in perspective, 1 part in 10 to the 21st, roughly speaking, for the first source that we detected. The nature of the wave is that it stretches space in one direction while it compresses in the opposite direction, and then it oscillates. So, now moving closer to the tinkering. So how do you measure this? Well, there's an interferometer called the Michelson Interferometer, and in its simple topology, it's basically a laser that goes to a 50-50 beam splitter. Half the light goes through, the other half is reflected. It goes to an end mirror that reflects the light back. Those end mirrors are also masses, and we arranged for them to be free to respond to the gravitational wave. So this is an ideal geometry for detecting gravitational waves. It gets a little more complicated to actually carry this out at the extreme sensitivities required. That is, we're measuring subatomic dimensions over long distances to amplify the strain. So we have 4-kilometer long arms to amplify that strain effect. To amplify it further, we put input couplers so that we bounce the light many times, about 100 times in each arm. So it's resonant for quite some time. And that effectively amplifies the length of the arm, which minimizes the civil construction costs considerably. In addition, we recycle the power that would otherwise reflect out of the interferometer and be lost. We put a couple cavity in front here so that we can build up powers close to a megawatt in each of the arms. In addition, we tailor the signal on the output side of the interferometer by, again, broadband recycling. So there's two common ways to characterize the sensitivity of this instrument. We generally, the tinkerers, the engineers, think of it in terms of the strain per root hertz, that is the amplitude spectral density as a function of frequency. And in this space, in this way of representing it, we're limited by quantum shot noise at high frequency and quantum radiation pressure at low frequency. And also technical noise sources like our ability to isolate from the seismic noise of the ground. In between, we're limited by thermal noise or Brownian motion. And the other way we represent it is the range, the volume of the universe that we can sample. And I think in the interest of time, I'll skip over that. So looking at it in terms of the strain amplitude spectral density, here are three of the signals we've seen. These chirps whistle through our interferometer. We can't measure it anything lower than 10 to 20 hertz or so. And they sweep up until they coalesce and then ring down into this new black hole object. So this is gives you kind of the idea of the signal to noise that our interferometers can detect for these events. Okay, now I'm going to go into the engineering, and this project, as you might imagine, covers a lot of different technologies. And I'll give you a smattering in the sense of what's involved. Starting with your observatory site selection, there are a lot of criteria that went into selecting the two sites, but suffice it to say that one is on cheap flat land in the high desert in Washington State, and the other is cheap flat land in the swamp in Louisiana. But they're widely separated so that we don't have common environmental effects like a lightning strike or glitches on the power network that were shared by the interferometers. We felt strongly that this was such a difficult measurement, we had to have two observatories detect this simultaneously for the first event. Since then, now that we know these events are real and we know the signature and the characteristics of them, we are now confident with high signal to noise ratio events to declare detection with a single detector. So the facilities are also non-conventional. We separate the HVAC handling from the building. We take great care to make sure that none of the materials or the machinery have outgassing products that could get into the environment and spoil the pristine optics that we put into this interferometer. We also pepper the facility with instrumentation in order to veto any events based on environmental sensors. So we have magnetometers, seismometers, accelerometers, microphones, gamma ray detectors throughout the observatory to make sure that we're not fooling ourselves. The vacuum system, both of these observatories have two of the largest ultra-high vacuum systems in the world. They're, as I said, each arm is 4 kilometers long, so 8 kilometers of 1 meter diameter pipe at 10 to the minus 9 torque. And those were built with, at the time, and I think even now, rather novel construction techniques that had to be proved out in order to drive the cost for the system down to reasonable levels. We need to keep the mirror absorption to less than 0.7 of a part per million, and to do that we have to have extremely clean systems, both from a hydrocarbon outgassing standpoint, but also from the standpoint of particulates. This is some of the pictures showing the scale of the project to mobilize factories that were built near site and brought just in time to weld the sections of tube. This is over 50 kilometers of weld with not a single vacuum leak. And I can tell you now that we've had problems with leaks, and they're not easy to fix, to find. We also, at one point, thought, well, maybe we won't need to cover the tube. Fortunately, we did. There have been some events that could have knocked the facility out for a long period of time. More recently, just to give you a sense of the kind of scale of the problems we have to deal with, they're not just cutting edge, leading edge technology, but we have in Louisiana a wet environment that focsters microbes, and this was new to me, that like to eat steel, stainless steel. So we have microbial-induced corrosion that have caused now 3 different leaks. They're quite small, they're about 10 microns in diameter through the 6 millimeter thick wall of the tube. But when you're trying to hunt for that 10 micron diameter hole in 4 kilometer tube, I can tell you it's a very difficult problem. The other very difficult problem is to handle the seismic environment, or the vibration isolation. This graph shows the different span of frequencies over which we care about isolation. We have, as does everyone, a microseismic peak that has to do with the oceans landing or waves hitting the continental shelf. And this propagates throughout the continental land masses. So a thing known to geophysicists, but not often a problem, except for very sensitive instrumentation. And what we need are on the order of 10 orders of magnitude of reduction in the isolation. So how do we do that? Well, we have 7 sequential stages of both active and passive isolation, starting with a custom-designed, quiet, laminar flow hydraulic pre-isolator that handles 6 degrees of freedom. And then on the next 2 stages, they're sprung stages, that is, they're on springs and flexures with electromagnetic actuators and inertial sensing to provide the isolation. Then the final stages are, before I go into the final stages, here are some pictures just to give you some scale of these isolation systems. This is for the larger tank. This is for the smaller one, where objects are placed on the top of the table. Here, this is an inverted table, and the optics are hung underneath. And those optics are 4 stages of pendulum, sort of like marionetta, that hold ultimately the test mass, or the optic in the resonant cavities, optical cavities. There's a second isolation stage behind that because we have to actuate on the mirrors in order to bring them into optical lock, and that requires a very well-isolated reaction mass, if you will, for the force actuation against the mirrors. Some pictures of those stages. They're hung on fused silica fibers that are welded to ears that are epoxy silicate bonded to the, not epoxy, I'm sorry, silicate catalysis bonded to the fused silica optics. The optics themselves are exquisite. These are 40 kilogram masses of ultra high purity fused silica from Heraeus in Germany. They're polished to 2 kilometers radius of curvature with figure error that's less than 3/10 of an nanometer in error. We do that through super polishing and then ion beam etching. Then they're coated with multi-layer dielectrics that are designed to be ultra low in loss, that is mechanical loss, or Q. We do that with special tantalum dope, titanium dope tantalum pentoxide. The laser was a contribution from Germany. I should have mentioned that the quad suspensions came to us through contribution from the United Kingdom, principally worked on by the University of Glasgow. The Albert Einstein Institute in Germany provided the laser system. It's a multi-stage amplifier system. It starts with a master oscillator that generates a 1064 nanometer. It's a Nadidium Yannick laser. This is about 200 watts. We've since, because of some reliability issues with this last high power stage, we've gone to a different configuration for that amplification, but and we're exploring alternatives. This is just some pictures of the laser system. It's in its own separate acoustic shielded building, if you will, within our main instrument hall. So this is, in many respects, a very large controls problem. We have a number of different plants. There's the pre-stabilized laser. And I say pre-stabilized because there's a hierarchical system in which we first lock it to a local reference cavity that's temperature stabilized, and then to sequential optical cavities until finally the frequency of the laser is locked to the average of the 2 arm cavities. Those are the quietest, most well isolated. The seismic isolation system, as I said, is 7 stages of isolation. Each of the active stages has 6 degrees of freedom, so it's 18 degrees of freedom on about 10 isolated platforms. The suspensions themselves are designed so that all of the modes in that marionetta are sensed and controlled from the top by design. So it's a very complex multi-input, multi-output system that has both feed-forward and feedback. The main interferometer length control requires RF modulation. The cavities, if you were trying to, what we call it locking, optically locking the cavity, which means you bring it into resonance and you hold it on resonance. The signal for that you might think would be the power that leaks out of that cavity. But because these optical cavities have very high finesse, it's the optical equivalent of mechanical Q. It's a very narrow bandwidth. It's very, very small motions in the positions of the optics allow one to get to resonance, less than a wavelength of light. So it's difficult to find that spot. Moreover, that signal is not a null crossing signal. It's not linear. So to solve that problem, we borrowed technology from microwaves. I think invented back in the late 1940s. You look at the reflection from the cavity, and you RF modulate, look at the sidebands and their phase response. You can then get a linear signal that crosses through zero. So we have multiple radio frequency modulations that we apply to the laser before it's injected into the system. And then we have various optical ports that we can read out the signals and demodulate them, and then use that in a complex matrix that's often quite sparse in order to provide length and angle sensing of the degrees of freedom of the interferometer. There are other complexities. Radiation pressure can cause instabilities. They're again handled through control, feedback control. The optical modes of the cavity are very similar to the mechanical modes, the vibrational modes. And if they overlap, they'll beat with each other and pump energy into the acoustic modes. We solved that initially through active feedback control, through electrostatic actuation. More recently, we've designed piezoelectric dampers that are passive, and the key here was not to spoil the high mechanical Q, low loss of these exquisite optics. Then there's squeezing, and I won't pretend to know a lot about squeezing, but in order to try to improve the quantum noise at high frequency, so-called chop noise, we use squeezing rather than increasing the laser power. Increasing the laser power can be done, but it brings with it a number of other problems, including increased photon pressure noise that jostles the optics and makes them move at low frequency, but also, despite the fact that each of these optics are very low absorption, they do absorb and have thermal deformation, so you have to compensate. I won't go into the architecture for the hardware and software, but except to say it's fairly common. It's not, it's cutting edge, so to speak. We do our own hard real-time patches to Unix, but it's not terribly unusual. Same is true of the software architecture. We do have our own, what we call real-time code generator that is based on Simulink that we use to interface to what we call EPICS. It's borrowed out of the high-energy physics community for parameter control of this very large system. The state machine we use for sequencing we call Guardian. It's a distributed hierarchical finite state machine that's custom code built in Python. It's important because this is a very nonlinear system that requires very careful sequencing through the various cavities that have to be locked up. It's a very nonlinear controls problem. So let me finish with a few thoughts on, from my perspective, how can engineering help big science? I won't pretend to know small science. Stakeholder buy-in is very important. This project took, well, I've been working on it for 24 years, to give you a perspective. There were others who joined the project earlier than I. So that's on the order of, prior to my joining, 15 years or so. It's a 40-year project. Started with Caltech and MIT doing investments. But it required the vision and persistence of those stakeholders, the two institutions, and then the National Science Foundation. It required system engineering, which in this community, particularly growing out of a small-scale laboratory physicists, they were a bit resistant to having trade-off studies and detailed requirements defined, QA, QC, etc. All the things that engineering can bring to make a viable project. You also have to push the state of the art quite often. And to do that, you need to align yourself with others who have the same interests, hence the very large collaboration we have. You need to develop pathfinding for key technologies, particularly if they involve processes out of industry, so that they can work through the problems early enough that you can identify solutions. You have to... Oh, okay.
So,
all right. I'll just conclude by saying that the innovation and complexity we handled in various ways, some technical, but a lot of it was through inclusion and openness, which you've heard as a theme here, hence the very large scientific collaboration. You have to give up some control, and you have to have more people on your authorship papers, but it's well worth it in the end. And we're now facing, as a community, once again, getting everyone behind a single project. We're now, the community is looking at trying to build the next generation, which will be billion-dollar class instruments. And to do that, you really need governments and the entire community behind a single idea and group.
thank you, Dennis. Thank you for this short introduction to gravitational waves and showing us the fascinating complexity of what you're doing, of the interference of mice, seismic waves, and everything. That was very interesting. Thank you very much.